We left off the other day looking at the four quantum numbers. The principal quantum number is that value. Let me write this in here. Principal. All right. So that principal quantum number is referring to the energy level in which you find these electrons. So if we're thinking of it in terms of a Bohr model, you're looking at the energy levels, and you can find that on the periodic table as the different rows that you'll find numbered. Now remember, I left off at the very end saying that not all of your periodic table is arranged based on electron configuration, because what we'll find here today is that these 3D sublevel, those transitional metals, these electrons are actually going to be located on the third energy level if we were to draw out a Bohr model. We have the shapes. That would be your angular momentum. The angular momentum refers to, if we have an electron distribution that would look like this, that would be called an s orbital. We have the ones that, it kind of looks like a figure eight, infinity, dumbbell, however people want to describe it, but you have those distribution densities that would look something like that. And we could continue on to looking at the d orbitals and the f orbitals also. You have the 3D orientation. The 3D orientation, you have that magnetic quantum number, and that is referring to the orientation in space. So this would be like the px, this would be the py, and this, if we could draw that coming out of the screen at you, that would be the pz. And then lastly, we have the direction. The direction is our spin quantum number. The spin quantum number, we are going to refer to them as an upspin or a downspin. Some refer to it as a plus, 1/2, minus a half, clockwise, counterclockwise, but we're going to use the up and down notation. That's what we're going to do. These four quantum numbers, when we're filling in the pictures of these modern atoms, it just becomes a giant blur. If we were to try to put the s orbitals and the p orbitals together, you can see if we start doing that, it just becomes a giant mess. All right, so what we're going to do instead is we're going to describe where these electrons are going to be positioned. All right, so the thing I want to warn you of in advance is that when we are filling in these electrons, trying to describe where they're at inside of the atom, it doesn't fill in nice and neatly. Sometimes what's going to happen is those they're actually nodes. These regions are going to start overlapping each other. So we'll try and look at the best way to describe that, the easiest way for you to understand what's going on. To do so, there's certain rules that you have to follow. There's 3 of them. The 3 rules that we have to follow when we're putting in the electron distribution is the Offbow Principle, Hund's Rule, and the Pauli Exclusion Principle. Those 3 rules are going to tell us how those orbitals, the electrons, are going to fill into them. Okay? So let's start off with this Offbow Principle. That is describing where the electrons are going to enter with the lowest amount of energy first. Now, you can think of this as, let's say that you have a cup. All right. Now, if you just had one cup and you were going to fill it with water, you know that it has to fill from the lowest, and then it starts to gradually move upwards from there. All right, so we're filling the cup from bottom up. Now, if we had a second glass that we were going to put in here now, all right, so if we were going to put that second glass in, you know that as you pour the water in, that water has to get to a certain height, and then we can start to fill in the other. All right, so when you are looking at filling in these electron placements, you have to fill in from the lowest energy state up. Now, I was always taught with this personally, I think it's a horrible method. You label out your s orbitals. You say 1, 2, 3, 4, 5, 6, 7 s. So those are your rows on your periodic table. Then you go your p orbitals. You fill those in and so forth. Now what they do is with like a diagonal rule, you're supposed to fill in the 1s orbitals first. Then you'd fill in the 2s, and then we'd go 2p, and then 3s, 3p, then 4s like this. Now, if you like that, go for it. You remember that filling order from the lowest energy state up. But personally, I think if we look at our periodic table, and let me go back and grab one real quick. So we'll grab this. And if it moved just a little bit faster for me. One more time. There we go. All right, so personally, I think the easiest way for you to remember this, if we have the S block over here, this is our S block, and over here you have your P block, and then we have our D block here, and then we have the F block down here. If we just treat these as if we are reading a book. So in order for us to read a book, we always start at the top and read from left to right. So that means when we're filling this in, we have the 1s orbital that gets filled first. And there's 2 electrons that can fill in there. Now, once you're done with the first line, what do? We go down to the second line in our book. And we read from left to right. And if we're reading from left to right, right here, this is that 2s right here. And on the right side, if these were the p's, if this block right here was the p's, that would be on the second row, and they'd be the p orbitals, those dumbbell-shaped ones. Now, once you get finished with that, you go down to the third row in your reading, and when you get to the third row in your reading, the first thing you see is the 3, and these 2 right here, where are they at? They're inside an s orbital, so we say 3s. You come over to the right-hand side now. If we're looking at right here, these 6 elements right here, you would find those on the third row, and they're inside of the P block. This is where we're going to have some filling order discrepancies. See, when we go down here to the 4th row, and we're going to read across, right, like this, just like we're reading a book, all right? So you have, obviously, the 4th row. The first 2 that we find right here, that's going to be the s orbital. That's that S shape, or the spherical shape. Now, this is where I said that your energy levels don't match up perfectly. They start to overlap each other. If we were to look at the distribution patterns that are created, we would see that the 4p over here does not get filled up first. Right? If we're thinking about these in terms of energy, the 4s requires less energy to fill than it would for the 3ds. So these right here, this would be the 3d. Now, how can you easily remember this filling order? Well, if we look at the bottom, I have little cheats here for you. All right, so if we're looking at this, you can see down at the bottom, you see right here, it says 4s. And then, before we ever see anything with a 4p, you're going to see right here, 3d, 3d, 3d. So that is going to get filled up before, you ready? We come over here, and then take a look. Now all of a sudden, we start seeing that 4p in here. All right, so if you read it like a book and you use my periodic table the way I want you to, you're going to know that the 3D orbitals are going to get filled first before the 4p. All right, and again, we're talking about energy associated with filling these orbitals. It's easier to fill that 4s than it is to fill the 3d. So that distribution pattern, those nodes that are created when we're looking at this, that's what's going to happen. Now we go down here to the fifth row right here. So if we look at this fifth row right here, we have 5s. Why 5s? Because the first two are always found in that spherical shape. Now, if we're reading like a book, even if you don't use the cheat down at the very bottom, if this one right here, if this was the 3D, then it would make sense that this would be the 4D here. And then we're going to come over here, and then we're going to go back to our 5P. And you can always check that because, see, you're going to see 5S and then 4D, but you don't see any 5P yet, do you? We come over here, and we start getting into the P block, and now all of a sudden, you've got your 4D, 5S, and right there, you got that 5P. So then we can start filling those things in. We will get down into this next group right here. So this is going to be maybe easier for you to understand. If we're looking at this, our lanthanide series was pulled out down here. Why? Because we don't want to have an expanded periodic table, something that we have to roll out in order to see what's going on with the things. So maybe what we could do is do this. If we're looking at filling in that sixth energy level, all right, so we'd have to come across like this, right? So we come across, and here you'd have our 6. Ooh, that's huge. Let's go. This would be our 6S. We'd right here have our 4F, and then we'd have our 5D, and then we'd go back to our 6P. Now that's getting extensive. We aren't going to have any elements that are like that, but just so that way you know how to read it. And it's not that difficult because if we're looking here, you can see it says 6S right here. And then what do we see popping up? Look at that. We got our 4F, and you have that 5D that I was just mentioning. Okay. For up here, you got your 5Ds. So that is when we're looking at the electron arrangements. When you are trying to fill in those electrons, we always fill from lowest energy state up. All right, so remember, Offbow, fill from lowest up. We talked about our reasoning whys. Let's take a look at our second rule. The second rule is called Hund's rule. Hund's rule, oftentimes you're going to hear it referred to as the empty bus seat rule. All right, now why is that? Well, let's take a look at an example. I need an extra paper here. We'll add. Boom. Here we go. So the empty bus seat rule. Let's take oxygen here as an example. Now oxygen, we know that oxygen has that 8 electrons, right? Its atomic number is 8. So if we're looking at the number of electrons that a neutral oxygen would have, it would have 8. If we're filling these things in, we have 8 electrons. Let's do a Bohr model of this first. All right, so it's found on the second energy level. We have 8 electrons we have to fill in. We know that 2 can fill in for the first. And then when we're filling in the next ones, all right, oop, I got too many in there, don't I? We got 2, 3, 4, 5, 6, 7, and 8. There we go. I don't think I had too much. I think I had too few. So if we have that number, now that would be, again, if we're looking at our periodic table, okay, I know that I'm right in terms of number of valence electrons because, see, look, it is in the 6th column, group 6, so we should have 6 outer electrons. All right, and I'm going to grab this. We're going to use this because I like this idea. So if we have 6 outer electrons, we count up our electrons and we have 6. We have to fill in that electron distribution now because a Bohr model is not our correct model. And what we need to do is describe, because it's not real easy to draw out, but we're going to describe what we see. So on the first row, the first two electrons, all right, what are we going to look at? Well, right here, filling in this first row, we have from left to right. We're going to read this like a book, right? So we're going to read it from left to right. That means that you find the first energy level. So right here, that's energy level. We're going to have 2 electrons, and then we go down to the second row. You have 2s. That would be, if we're filling this in, 2s, and then we're going to come across until we get to right here. All right, so in that 2s, you have 2 boxes, 2, and we're going to do more of this electron configuration in just a little bit here. We're just trying to fill stuff in. We come over to, what's this block right here called? That's called the 2p. You have 1, 2, 3, 4. So we go 2p, there's going to be 4 electrons. Now, those 4 electrons, if we do a diagram of where these things would be found, all right? Now, we're only going to record the outer electrons for right now for this. So, let's do this. No, well, we could do them all here. So if we look at this, and then the p's, remember the p's here, this is an s orbital, you have the p's, remember that the p's, there are 3 of them. You have the px, that lies like this, you have the py, that is like this, and then the last one, if we could draw it coming out of the board at you, it would look like that. All right, now, we're going to get to Hund's rule, just bear with me here. Electrons, when we're looking at filling in orbitals, we always want to fill in half of it before you'd have to double up. You can think of it as you're on a bus and there's some stranger sitting in a seat that maybe smells or you don't like the look of them or something. Maybe you just are a little shy. You're not going to sit with them. So when you get into, let's say, this small bus right here, all right, there's only one bench seat in the bus. So when we start filling in electrons, these 2 electrons that are going to get filled in here, we have 1, and then there's nowhere else for them to sit, so there's 2. All right. So each one of those electrons, do you see how I drew those? So those 2 electrons, 1 an up spin, drew an arrow up. 1 a down spin, that's the second one. All right. So we go into the second bus. Now each one of these, you can think of like an s orbital as like a bus. So it's just a small 2-seater. You have right here, you got 2 electrons, 1, 2. Now the P bus here, the P bus, we have 3 bench seats in it, right? So there's 3 bench seats, and you have how many electrons that are going to fill into this? You've got 4 electrons that are going to fill in, right? Now the other 2, if they were just 2-seaters and you had 2 electrons to fill in, well, that's all that they can seat. You can't put 5 or 6 people into a 2-seater car. Here, we're looking at putting in 4 electrons into the p orbitals. So, this is how it goes. There's 4 of them. The first passenger hops into the bus, into the first bench. All right, now this bus has 3 benches, the PX, the PY, and the PC. All right, so you have 3 benches here, and the first electron gets in, sits down at that front seat. So we have now 3 that we need to fill in, right? 3 more. So that second electron comes in, all right? So this is our second electron right here. The second electron, he comes in and says, "Whoa, I'm not going to sit next to this dude. The guy looks a little weird. So I'm just going to sit into an empty seat." So that second person goes into that empty seat. So now you have 2 more electrons that you have to fill in. So The next electron goes to get picked up by the bus. Whoa, that dude looks a little weird. And then he comes over here, and this one's giving him the winky eye. We don't want to sit here with this person, so what do? Boom. We go to the empty seat, the empty orbital. So these electrons, if you don't like this analogy, electrons that you can't take and have two things pairing up when they're, let's say that they're negatively charged and you're trying to force magnets together. If you have the similar charges, they're going to repel each other. These electrons don't want to pair up unless they absolutely have to. So we have one more electron that's going to get put in here, and the last electron, here's the issue that you're going to have with this. See, when this electron gets in here, no empty seat, no empty seat, no empty seat, because each of these are half filled. Now, this electron has to find a spot to be placed in, but see, look, you can't have two with the exact same spin. All right, we have to have unique quantum numbers, and this guy right here, we can't have that. So what happens with this is this guy forms what we'd have as a, or if I could draw this, come on now, work for me. There we go. Is going to have an opposite spin. All right. So there is introducing our spin quantum number right here. So that is our Hund's rule that we cannot take and fill in a second electron into an orbital unless all of the rest are going to be half filled. Okay. So we have our Hund's rule. Let's go to our next thing here. We go to our next one, and we have what's called the Pauli exclusion principle. So at most, only 2 electrons can fill per orbital. We've mentioned that many times. So in order for those electrons to fill into those orbitals and double up, they must have, and this is why I drew one of them with an up spin and then the other one with a down spin. They have to have different spins. We have to have unique IDs for every single electron. And it's kind of like that analogy that I've used with you getting a ticket to like a baseball game, football game, concert. Everybody has to have their own unique seat number. No one can have the same 2. So let's review real quick before we're finished up here. You have the 4 quantum numbers. You have the energy level. That's going to be your principle. You have your angular momentum is the shape. You have the magnetic is the orientation. And then we have the spin. That is going to be either that up spin or down spin. The principal quantum number, it's referring to your energy level size. So you have the first that's smaller, second gets bigger, third gets even bigger than that. All right? We can use the formula n squared to help tell us what the number of different orbitals we're going to find in each energy level. That works real well all the way up to the 4th one. And then when you get to the 5th, we don't have enough elements known to fill in any of those extras. The angular momentum is referring to our shapes, and those shapes, we can find them on different energy levels. So you have only the S in the first energy level. Then on the second energy level, you can find the S shape and the P shape. On the third energy level, you can find the S's, the P's, and the D's. And then when we get to the 4th energy level, you can find the F's, the S, the P, the D, and the F. So this is like the 1st, 2nd, 3rd, and 4th like this. All right. We have our magnetic quantum numbers, and this is that orientation in space. Now the nice thing is you're not going to have to worry about these D orbitals here. If you just think of it as the px, the py, and the pz, that'll help out a lot. The quantum numbers, when we're filling in these electrons, not everything is going to go right perfectly in line. You're going to get energy levels like this right here. You'll get things that are going to start overlapping each other. All right, so expect that to happen. And if you read it like the periodic table like a textbook, you're going to have no problems. Our spin quantum number is going to refer to the clockwise or counterclockwise spin, plus a half, minus a half, up or down. Those are just different ways that you can describe that fourth value. When we're writing these out, and this is what we're going to do probably tomorrow, if not maybe start today, depends on how much time we've used up here. When we're writing these things out, I introduced this already. We're going to write out the electron configuration for these by simply placing in the front which energy level we're finding the elements on. The second thing is going to be what shape of orbital are we going to find them in. And then the last thing is the count of the electrons in that particular orbital. So with hydrogen on the periodic table, we're going to go back to it. Ooh, I should get a couple more of them in here. So if we're looking at hydrogen, get rid of all this stuff here. All right. So hydrogen, we're looking at this guy right here. Well, it's on the first row. This block right here is called the S block, and you only have to count over one spot. So it's 1s1. If we go over here to helium now, with helium, and I'll put this, we'll say that's hydrogen. That's what hydrogen would look like. With helium, if we read this like a book, right, what row is it on? It's on the first row. What type of shape do we find it in? Well, if we come over here like this, that's in an S shape. And then how many boxes? 1, 2, 1s2. You go down to, let's say, lithium now. Lithium, Li. Now, filling the cups of water. This right here, this first row is already filled up, right? We already filled that up, so I'm just going to repeat that. So I'm going to put down 1s2 because that's already filled up. We're going to come down to the second row, 2. This block right here is an s orbital, and I count over 1 electron. See how easy this is? All right, a whole lot easier than drawing these things out. Let's go to our next one. Let's say beryllium here. Beryllium, the first energy level was already filled up. Can't put any more there. Okay. So we go down to the second row. It's an s orbital, but now you're going to fill in the second electron. Boom, right like this. Let's do maybe 2 more here real quick. So let's say that we're going to now fill in for, let's go carbon. Carbon, we know that the first row was filled up, right? We know that if I'm reading this like a book from left to right, I'd have to fill in these, this one and this one first. So that's where that 2 comes from. And then I'm going to go over to the right, and the right ones, that's going to be that 2p, right? This is the second row. This is the p block. And I'm going to count 1, 2 electrons. All right? So that's how we write out these notations for the different electron configurations for this. So, last thing we have for these notes is what would an orbital notation look like? Well, instead of us putting in the values of the number of electrons we find in each one of those, what we're going to do is we're going to put in the electrons for these. All right, so let's do that on our periodic table that we have up here. Here we go. All right, so with these values that we've just written out here, let's see how this would look if we had an orbital notation. This is what we call an electron config. Now what we're going to do is we're going to look at an orbital notation. Orbital notation, you have 1, right? First energy level. And then we're going to have S, and then how many spots can we fill in for that S? We can have 2 electrons, right? So we have 1, 2, right, like this. Right? So let's go to, that would be not 2 electrons. We only had 1, right? So only had 1. I knew something was off on that. So we go down to the second one. You have helium here. We have 1 S. We'd repeat that. Now, how many orbitals are there? There's 1 orbital. And now we have, let's get it right this time. We have 1 electron, 2 electrons. You have lithium. We have 1 S. Now, everything that was there before has to stay. Now we come here, we have 2 S. And then an S orbital has 1 orbital found there. And there's 1 electron. You have beryllium, 1s2, 1s, 1, 2. Second one, 2s, 1 orbital, 2 electrons, 1, 2. Opposite spins, Pauli exclusion. And then for this last one, you have 1s, there's 2 electrons. You have 2s, 1 orbital, 2 electrons, 2p. All right, the p's, remember there's a px, there's a py, and then there's a pz. You have 2 electrons, Hund's rule, 1, 2. They have to fill in like that. Okay? So, let's take a look at what else we have here, because I think we're pretty much done with this. We're going to start those electron configuration, writing them out. And with that, let's go with checking our time, and then I'll get back with you if I need to put another video out, okay? Submit your notes for this to the assignment, and that will get graded.